Good morning, everybody. This is Cal with sections 11.3, continuous functions, and 11.4, metric spaces. These are our last reading of the term. So, let me cover them briefly. So, in 11.3, our game is talking about continuity using point set topology. So, basically, we're going to redefine continuity using concepts of open and closed sets and so on. I would read I would read the introductory blurb on 337 and the blurb on continuity at the bottom. We we have this lemma 1131, which is a restatement of the neighborhood definition of continuity in terms of neighborhoods instead of epsilon neighborhoods. This should be relatively straightforward. Okay. From there, we develop a condition for global continuity, a condition for F to be continuous everywhere. And it's basically that this lemma happens at every point, but the statement is a little bit more elegant than that. So the global continuity theorem is that F is continuous at every point in A, if and only if for every open set G in R there is an open set H in R, so that H intersect A is F inverse of G. Now that's poorly stated. The way I would say this is that F is continuous on A if the pre-image of every open set under F is open relative to A. Its intersection with A is relatively open. We haven't talked about relative openness, but the idea is that pre-images of open sets are open. If your domain A is not funky, if your domain A is just R, then this is literally F is continuous if and only if the pre-image of any open set G, is open. So the pre-images of open sets under continuous functions are open. And this is actually taken as your definition of continuity in many more generalized contexts, which is what your book says in the middle of page 338. Okay. We can also view this another way. We have theorem 1134 here, which is preservation of compactness. It says that if K is compact and if F is continuous, then F of K is compact. So, excuse me, continuous functions take compact sets to compact sets, which is pretty great. In 1135 we have some applications, and these are basically some really easy reproofs of some earlier theorems that we had based on this preservation of compactness theorem. I would read those applications relatively closely. And then we have theorem 1136, which won't be so important for our purposes, but it's cool. If K is compact and F is injective on K and continuous, then F inverse is continuous on F of K. Now, we didn't really talk about inverse functions in this class, so you don't have to spend too much time thinking about this theorem. That being said, it is a cool result. So, all right, moving onward to section 11.4, we're going to talk about metric spaces, and this is meant just as a preview of some things that you'll see in 302. We've been working this entire class on R, and there's no reason that we have to be working on R as our basic space. And there's no reason that we have to use the idea of distance that we've been using on R. So here we're going to develop just some basic tools to work with some of the concepts of real analysis like we've had so far on more generalized spaces than just R with the standard distance metric. So you're going to want to read, starting at the bottom, this bit under metrics, pretty carefully. We have a definition of a metric. A metric is a function given two numbers in a set S. You want to have a notion of the distance between them. This is why we call it D. It's the distance between two numbers on S. And the properties that a metric needs to satisfy should make sense. First of all, distance between 2 points is always positive. Distance is 0 if and only if the points are the same. Distance is symmetric, so different distance between x and y is the same as distance between y and x. And distance follows a triangle inequality. Okay, so any set S along with a metric D that tells you how to find distance between points on S is called a metric space. And this is an extraordinarily important concept going forward in analysis. When you're dealing with analysis in 302 and onward, your first assumption in any situation is, suppose we have a metric space S comma D or something like that. I would read through the examples in 11.4.2 very, very carefully. These are all very common sets with metrics, and you want to have a certain amount of familiarity with these. I especially like the metrics that it presents on R2, so B, C, those are pretty cool. We'll talk about these a bit in class, of course. It has a couple of metrics on the set of continuous functions on 0 to 1, which is a metric space given an appropriate metric. I would seriously consider doing some of the homework problems where you verify that these things are metrics, that these follow the properties in 11.4.1. Okay, and the other one here is in F, the discrete metric, which is another pretty important one. Okay, so below that we talk about neighborhoods and convergence, and this follows exactly the way that neighborhoods work on R. It's just that you have a different way of measuring distance. So do read definition 11.4.3, 11.4.4, and again, series convergence looks exactly the same. It's just that we're using neighborhood language here. And I would read through the examples in 11.4.5 relatively carefully. Come on. Okay. Your book talks about Cauchy sequences using these new rules. I would, again, read through the definitions. Definition 11.4.7 is going to be an important one for you. A metric space is called complete if every Cauchy sequence converges. Now, in R, we know that we have the completeness property. In other metric spaces, it's a property of the space. A metric space may or may not have this completeness property. If you do have a complete metric space, then life is easier for you. And the examples below in 11.4.8 are relatively important. Then we talk about open sets and continuity. And so open and closed sets follow the same definitions that they did in 11.1. And our definition of continuity is going to be based on our open set characterization from 11.3. And you have a global continuity theorem. Preimages of open sets are open, which should mirror what we saw in 11.3. And we have preservation of compactness, like we had in 11.3. So you can see we get a lot of the same stuff that we had in R in this more generalized context. I wouldn't worry about semi-metrics. You can read it if you like. I won't stop you, but we're not going to worry too much about it. So you can probably ignore that last page of 11.4. And that's it.